So for this last couple of examples, what we're looking at is what's called erratic motion. And so that's where the motion of the object, so in this case I've got a little car here, changes from different stages. So for example, say for this car, the first stage might be that it's, ignore the question just now, I'm not thinking about this question, here we go, now you can ignore it. And so for this car here, the first stage might be that it's sitting at rest for 10 seconds, so it's got zero velocity, zero acceleration, and zero displacement. So we're going to take the displacement from the starting point. Then it might accelerate for maybe 5 seconds. So that would be the second stage. So it starts at rest, sits there for 10 seconds, then accelerates for 5 seconds. Then the next stage might be it keeps moving at constant speed for a while, and then it slows down to a stop at the end. And so we've got different stages. And each of these stages, inside the stage, the acceleration is constant, but the acceleration changes between the stages. So stage 1, sitting at rest. Stage 2, accelerating to a certain velocity. Stage 3 continues with constant velocity. Stage 4 slows down and comes to a stop. Okay, so that's this kind of erratic motion. But for this class, we're going to be assuming that within each stage, the acceleration is constant. So what it can be useful to do is to plot some graphs so you can get an overall picture of what the acceleration and velocity and displacement are doing during this, so for each stage of the motion. So let's have a go at that for this. Now there's two ways of doing this. One way is to think about the equations of motion for each stage and then just use those to plot some points and figure out what the graph would do. Or you can do it by looking at the area under the curve, similar to what we did for the shear force diagrams and bending moment diagrams. What I'll do here is I'll do both. And so first I'll start off by thinking about the equations of motion, and then I'll derive the same graphs just by considering the area under the graph. So let's work through that first. So we're going to have 3 stages. How many stages have we got? So we've got starts from rest, accelerates for 10 seconds, maintains a constant speed for 20 seconds, and then decelerates to rest again. So we've got 3 stages here. So let's just think about these equations of motion for each stage. So stage 1. So we've got acceleration is equal to 1.4 meters per second squared. Then we've got velocity is going to be equal to, so let's just do velocity at time t. So all of this is, in fact, all of these are at time t. So just change this. So acceleration at time t is just equal to 1.4 meters per second squared for this stage 1. The velocity for stage 1 at time t, so the equation is the velocity equals the initial velocity plus acceleration times time. In our case, so the velocity at time 0 is just 0, so it starts from rest, so it's just going to be 1.4 times t for this first stage. The velocity at time t is just going to be 1.4 times t, and then the displacement at time t is going to be, so we've got initial displacement plus initial velocity times time plus a half times acceleration times t squared. So in this case, how much space? I should have enough space. It's just going to be equal to, so our initial displacement is 0, initial velocity is 0, so it's just going to be a half times 1.4 times t, which is just going to be 0.7 t squared. I don't know how many times I'm going to do that. So that's the equations of motion for that first stage. Now, for the second stage, what we're going to do is we're going to redo our time, and we're going to do that time starting from the beginning of the stage. So for stage 2, so let's do, we'll just say reset t. So we're basically resetting that time value to the start of this stage. Now, we can start to figure some stuff out using these equations of motion. So we're going to know that it's going to accelerate for 10 seconds. So the acceleration at 10 seconds is just 1.4 meters per second squared, but the velocity at 10 seconds is just going to be 1.4 times t, which is going to be 14 meters per second. So that's the velocity at the end of this stage, and the displacement at the end of this stage. So the displacement at 10 seconds is just going to be 0.7 times, so 1.4 meters per second is 0.7 times 10 squared, which is going to be 70 meters per, 70 meters is displacement, so 70 meters, so 0.7 times 10 squared. I'll try and write that so you could read it. Okay, so we've reset t for stage 2, and so we've put the t back to 0, and so this is after 10 seconds, but we're going to, it's like pressing the button on the stopwatch, we're just going to reset t. Otherwise, you can stuff around making these equations a bit more complicated, but I don't want to get into that here, so we're just going to reset t. So then we're going to have, for this stage, the acceleration at time t from the start of the stage, so t from the start of the stage is just going to be 0, because it's saying it's maintaining constant speed for 20 seconds. So a of t is going to be 0. Then we're going to have the velocity at time t. It's just staying constant speed, and so it's just going to be 14 meters per second, because that's the speed we got to at the end of the first stage. And the displacement at time t is going to be the displacement at the start of the stage plus the velocity at the start of the stage times the time from the start of the stage plus a half times the acceleration times time from start of stage squared. Now, S naught, we just calculated that, it's going to be 70 meters. Then V naught times T, so it's 70, let me not put my units in the equation, plus, so the velocity at the start of the stage was 14 meters per second, and I times that by t, and it's constant velocity, so the acceleration, this should really be a naught, the acceleration is just going to be 0, and so this whole term is going to disappear. So the displacement at time t is just going to be 70 plus 14 times t. So at the end of the stage, we're still going to have, so velocity, and it goes for another 20 seconds. So the velocity at 20 seconds from the start of the stage is just going to be 20 seconds. And so the velocity is constant, so it's just 14 meters per second. And then the displacement after 20 seconds, this is all, remember I've reset t, this is from the start of the stage. So the displacement after 20 seconds after the start of the stage is going to be 70 plus 14 times 20, which is 280 plus 70, 350, I think. 50 meters. Double check that, my mental arithmetic is terrible. Plus 14 times 20, 350. Then stage 3. I'm going to put a couple of exclamation marks near there. So for stage 3, again, we're going to reset t to be from the start of the stage. We'll figure out what the t is from the beginning as we draw the graph, but at this stage, we're just going to reset t. Again, we're going to reset t. So for this stage, we're going to have the acceleration at time t from the start of the stage is equal to, it's decelerating, so it's minus 0.5 meters per second squared. The velocity at time t, so we're getting that equation of motion, is v naught plus a naught times t. And so that's going to be, so the acceleration at the start of the stage we figured out down here, it was 14 meters per second. So that's going to be 14 minus, because the acceleration is negative, 0.5 t. We could probably fit that up here, I think. I might just bring this whole thing across just so we can fit everything in easily. Then we're going to have this displacement next. I'm just going to tidy things up a little bit so it looks the same for each stage. So then we're going to have the displacement at time t. The standard equation is the initial displacement for that stage plus the initial velocity for that stage plus the time from the start of the stage plus a half a naught t squared, which in this case, so the displacement at the start of the stage was 350 meters. We have that down here. The velocity at the start of the stage was 14 times t. And then, hold on, what am I actually doing here? Yep, the velocity at the start of the stage was 4, that's correct, plus, and it's not plus, it's minus. So minus a half times the acceleration for this stage is 0.5 times the time from the start of the stage. So that is equal to 350, wish I would stop putting my units into these equations when I don't need to, plus 14t minus 0.25t squared. So what can we figure out next? We'll leave it at that for now. We'll work our way through it. So what we don't know here is, we're saying it decelerates at 0. Easier to see it when you do the graph. So let's start working through these graphs. So we've figured out I might just zoom out a little bit so I can keep those in shot. So for our acceleration first, and how many seconds are we going for altogether? So the first stage is 10 seconds, second stage is 20 seconds, and then we don't know the length of time for the last stage, we just know that the velocity reduces to 0. So I think it is worth figuring that out. So we know that the velocity is going to reduce to 0 by the end of this stage. So V for the end of that stage is going to be equal to 0. Okay, so at the end, this is going to be equal to 0, so therefore this thing here is going to be equal to 0, which equals 14 minus 0.5t. So therefore, 0.5t is 14, and so therefore the time is going to be 28 seconds. So that's the length of this last stage. It's going to be 28 seconds long. And that makes sense. So we've got accelerated up to 14 meters per second, then we're decelerating at half a meter per second. And so it's going to take 28 seconds to get back down to 0. So the length of each stage, 10 for the first, 20 for the second, 28 for the last, so 58 seconds we need altogether. And the maximum acceleration we've got is that 1.4 meters per second squared. So that can work out okay as well. How many, what did I say, 58? So we could do 10, 20, 30, 40, 50, would be 60. I reckon that's probably the way to go. Just need to make this a wee bit longer. So we'll do 10 seconds, 20 seconds, 30, 40, 50, 60, and this is the time in seconds. And up here we're going to have, so we'll draw acceleration first, acceleration in meters per second squared, and we're going to have 0.5, 1.5, because we know the maximum acceleration we've got was 1.4 meters per second squared. 1.4, that makes sense, yep. So for 10 seconds, the acceleration is 1.4 meters per second squared, so we can draw that on first. Then it goes at constant speed, so it drops to 0. And it continues like that for 20 seconds. So it's going to get all the way to 30 seconds. Then, that wasn't really very well drawn. You won't even see it. It's on top of that line. Then the acceleration is going to, for the last stage, is minus 0.5 meters per second squared. And then it's going to keep going like that for 28 seconds. So we're going to get all the way to 58, which is going to be here somewhere. And then it's going to drop back to, it's going to stop again. The car is going to stop, so it's going to drop back to 0. And so this is 0.5 meters per second squared. Okay, then we want to do velocity next. So let's have a look through. So it's going to accelerate up to, after 10 seconds, it will be going at 14 meters per second. And it's going to be a straight line. Why do I know that? You can imagine for each second here, 1 second it's going to be 1.4, 2 seconds it's going to be 2.8, 3 seconds it's going to be 4.2. So it's increasing by the same amount each time. So we've got a straight line here inside this one. Then the velocity is going to be constant for this stage. It's going to be constant at 14 meters per second for the whole stage because it was moving with constant velocity. It must be in dynamic equilibrium. And then in this stage, the velocity is given by 14 minus 0.5 t. And again, this is going to be a straight line. So it's going to go, this is going to drop by half a meter per second every second. That's what it's showing you here. So each second, it's 1 second, this is going to be 0.5, so it's going to be 14 minus 0.5, then it's going to be minus 0.1. And so each second it's dropping by the same amount. So again, it's a straight line. And the maximum we got to was 14 meters per second. So let's draw that. We'll do it here. And it's all going to be positive. We don't have any negative velocities here. It just accelerates, keeps the velocity, and then slows down and stops. It never goes backwards. So we don't need any negative on that axis. So this is time in seconds. This is velocity in meters per second. And we've got 5, 10, 15 meters per second, 0. And then this is the same as above, 10, 20, 30, 40, 50, and 60 is here, and we're going to 58. So what's the velocity going to do? We already said it's increasing constantly, so it's 1.4 t, so it's going to be a straight line. So the velocity is going to be a straight line like so, and it's going to go up to 14 meters per second, which is somewhere there. Should probably measure it with a ruler. But I don't want to take too long to do this. Then it stays at constant velocity, so it stays at the same velocity for 20 seconds. So that's going to take us up to 30 seconds. And then it's slowing, it's decelerating, and it's decelerating by half a meter per second every second, because the deceleration was 0.5 meters per second squared. And so every 10 seconds it would drop by 5 meters per second. Is that correct? So it's decelerating at 0.5 meters per second squared. So every 10 seconds the velocity is going to drop by 5 meters per second. And so you can imagine that it would be like this: drop 5, drop 5. And so it's a nice straight line, and it's going to get down to 0 by the time it gets to 58 seconds, which is what we calculated above. And so the velocity profile is going to look something like, or it's going to look like that. Now, you could have done this another way. You could have just said, look, velocity is area times time, and so the change in velocity between any 2 points is the area under the acceleration graph. So for example, from 0 to 5, we would have 1.4 times 5, which is 7, that's correct, 7 meters per second. And you can see that's that point here, 7 meters per second. And then we're going to have the same area under this next 5 seconds, so it's going to go up another 7 till it gets to 14 meters per second up here. Okay, so you can either do it by figuring out these equations, or you can just have a look at the area under the graph. Here, the acceleration is 0, so the area under the graph is 0, so the velocity is not changing. Here, the area is on the negative side, so the velocity is going to be heading in the negative direction. And for each, say, we go along 5 meters here, then, well, even if, say, we go along 10 meters, the change in velocity is just going to be the area under between those 2 points. So the area under the acceleration graph between those 2 points. So that's going to be 0.5 times 10, which is 5. So every 10 meters you move along, it's going to go 5 meters per second, reduced by 5 meters per second. Okay, so you can do it that way as well, similar to the shear force diagram and the bending moment diagram. So for the last one now, we're going to do distance. Now this is one where it ends up being a curve, so it gets a little bit trickier. Let's just see where we're going to get to though. So initially we're going to go to 70, then we're going to go to 350 by the end of that stage. And then for this last stage, we haven't actually calculated that yet, so let's do it. So the displacement at the end of this last stage, ST, so it's going to be S of 28. So remember, we reset the time. So we're just putting this as the time from the start of the stage. It's going to be equal to 350 plus 14t minus 0.25t squared, which is equal to, I need to put in what t is, so 350 plus 14 times 28 minus 0.25 times 28 squared. So let's just calculate what that is. 350 plus 14 times 28 minus 0.25 times 28 squared. That's 546 meters. So we need to go all the way up to 546 meters. Cool. So let's say 1, 2, 3, 4, 5, 6. And again, the displacement's all going to be positive. It never heads backwards and goes past the point you started from. So it's not so bad. Time in seconds. Again, we just put on our call up the time along the time axis. And then here, displacement, in this case, displacement's the same as distance traveled. So then, now the issue here is, what we could do, that's 10, that's 5. It's a bit like when you're doing your, let's have a think, what are we figuring out? So say this was your shear force diagram. Interestingly, it's a V, it's a small v for velocity, large V for shear, capital V for shear. If this was shear, we're going to bending moment. If we had a line like this, you can see that the area under here is smaller than the area under here. So the rate at which it changes is increasing as it goes from here to here. So we could figure it out for each one. So at this point, we're going to have 7. This was 7. Let me just put this on grey. So 7. So that area there, am I jumping ahead of ourselves here? There is another way to do this. What we could do is we could use this formula. So we know that the displacement at time t is just 0.7 times t squared. Okay, so say we were doing 5, what did I say we needed to go up to? 546. So let's just label these first, 100. $200. Let me just pause just a second. So we've got those. Yeah, so what might be better is just before I start talking about the area stuff, oops, let's just ditch that for now. Let's go back and use the formula first. So we know in this first stage, the displacement is equal to 0.7 t squared. So let's just have a look at that first. So in this stage, displacement at time t is equal to 0.7 t squared. So that means at 5 seconds, the displacement is going to be 0.7 times 5 squared is 25. The displacement is going to be 17.5. So 50 would be here. 10, maybe 5, 10, 15, 20, 25, and up 10, 20, 30, 40, 50. So it's going to be around here somewhere. And we're going to have 0.7. So at 10 seconds, it's going to be 0.7, and it's going to be up at 70. So it's going to be around here somewhere. And you can see, and then it's going to be at 0. So you can see that that's going to be a curve. And so it's going to go something like that. And you could figure the same thing out from the area. So you could calculate the area of this little part first, and that would be the change in displacement as the area under the velocity curve. Then calculate the area of this part, and then figure out the change of displacement, and that would be this one here. So you can kind of choose whichever one you want. You can use the equations of motion, or you can do it by looking at the area underneath the curve. Now for this one here, again, we can use the equation. So for this one here, we know that the displacement at time t for this stage, when t is reset, so it's the time from the start of the stage, is equal to 70 plus 14t. And so that's for this next stage. So in that case, so after 20 seconds, we're going to have 70 plus 14 times 20, which is going to be 350. Let me just double check that. Oh, because it's going at 40. Yeah, okay. Yep, it's going at 14 meters per second. So after 20 seconds, or let's do 10 seconds. So 10 seconds after the start of this stage, it's going to be at 210. So the start of the stage, 10 seconds after that, it's going to be 210. And then 20 seconds after the start of that stage, just substituting into 70 plus 14t, it's going to be 350. So 20 seconds after the start of the stage is 30 seconds altogether. So it's going to be 350 about here. And you kind of know, well, how long as it goes up to 30, and that's the end of that stage. So that's the end of that stage here. And you can see that those are in a straight line, and that's expected because it's constant velocity. And so the displacement is changing at a constant rate. I haven't drawn it very well. Let's just have a look at that. I think that should have been a little higher, somewhere there maybe. And so we can draw those now. Then what's happening? So for this last part here, the displacement equation was displacement at time t is equal to, let's jump back up again, what was the equation? 350 plus 14t minus 0.25t squared. So it's equal to 350 plus 14t minus 0.25t squared. And it's the time from the start of the stage. Always with these ones, I'm looking at the time from the start of the stage. It might be better if maybe we call this T1, T2, T3. I'll maybe go through the working and just to make that clear. So this would be T1, all of these would be T1. It's just to make it clear that it's not the same, you're resetting that time. So that'd be T1, T1 here. And this would be T2 because we've reset that time. So it's a different time. It's starting from the start of this stage. And this might be T3. I'm just filling in T3 for all of those. And that kind of makes a little bit more sense. So probably better if we do it that way. And these would be similar. That would be T1, that's T2 from the start of stage 2, and this is T3 from the start of stage 3. So let's do some. So let's say 10 seconds in. So at 40 seconds altogether, we're going to get 350, take away 14 times 10, take away 0.25 times 10 squared. is going to be 185. So here it's going to be about 185, 50, 185 is about here somewhere. 20 seconds in, we're going to get 350 plus 14 times 20 minus 0.25 times 20 squared. What have I done wrong here? What have we done wrong here? Let's go back to that equation again. Sorry, I'm making a mistake here because this is still increasing. It's still increasing, so let me just recalculate that. I must have made a mistake. 350 plus 14 times 10 minus 0.25 times 10 squared is 465. So at 40, so 10 seconds into this stage, we get this is at 465, which is about 450, 465 is about there. Over there. 20 seconds into this stage, we're going to get 350 plus 14 times 20 minus 0.25 times 20 squared, which is equal to 530. So 20 seconds into the stage, which is at 50 here, and it's going to be 530. So it's going to be about here. And then 60 seconds into the stage, we're already calculated, 58 seconds into the stage, we'd already calculated it's 546. So 58 seconds is 546, so it's about here somewhere. And again, you can see that this time it's curving down the way. And we could have got exactly the same result if we had looked at the area. So the change in displacement is just equal to the area under the velocity curve. And so here you've got big area, and that's why there's a reasonably big change. But here the area is getting smaller. So we've got a smaller stage, areas get smaller again, you also get a smaller change again. Okay, and so that's the displacement time graph. Now, just checking I've got everything I need in there. We could put on some values here. So this would be 14 meters per second. And we could put some values onto this as well. So this here was 70 meters, was where at the end of that stage. And this here was 58 seconds, is where it ends. This value here at the end of that stage was 350 meters. And by the time you get to the end, you are at 546 meters. Okay, just so someone can check those results easily. Well, that was a bit mammoth. Let's go on to one more question and then we're done for the week and get on with the